This video is about autonomous rovers, especially looking into behavior-based autonomy and the different forms of intelligent rover architecture. To understand the differences of these designs, it is helpful to start with an example. Let's take a look at this problem. A rover is located at point A and should drive to our flag, point B. The distance to the flag is 10 meters. The first and most simple idea is to first turn the robot in the perfect position and then tell him to drive straight for 10 meters. Okay, great, but what happens if we can't drive straight to our flag because there's an obstacle, for example a rock, which we have to avoid? The most simple idea would probably be to hard-code the action. Turn to flag, drive straight for 3 meters, turn right 90 degrees, drive straight for 1 meter, etc. With this approach, we ensure that the robot's path is the most optimal path possible. However, the problem is that this architecture only works in perfectly known worlds, such as in a car factory, where the optimal time utilization of the robot is the top priority in order to save money. However, we quickly reach our limits with this method when the world in which we operate becomes increasingly complex, and the robot we use doesn't have a lot of computational resources. In addition, a robot, especially in space applications, should be able to move in unexpected or unknown environments, so we don't even have the option of determining a very precise map of the surroundings in advance, which the robot can use for his orientation. Nowadays, in which we manage to build artificial intelligence into Cubesat satellites, the very small satellites, and in which a single smartphone processor already has more than 120 million times the computational power of the first moon landing, this discussion may seem a little strange. But in the 1980s, when the behavior-based autonomy emerged, this still played a very important role. Okay, let's go back in history. In the early 1980s, the MIT scientist Rodney Brooks faced this problem. He wanted to build an autonomous robot, but only had a little RAM to calculate decisions, as the robot had to be quite small. While sitting around and looking up in the air, he then had an idea. I'm watching these insects buzz around, and they've got tiny little brains, some as small as 100,000 neurons, and I'm thinking, they can't do the mathematics I'm asking my robots to do for an even simpler thing. They are hunting, they are eating, they are foraging, they are mating. They are getting out of my way when I'm trying to slap them. How are they doing all this stuff? They must be organized differently. That's where he started to rethink the traditional robot architecture into designing the behavior-based architecture. This architecture is based on the most simple animal behavior, the reflex. A reflex in this case means a direct connection between the sensor and the actuator without difficult processing in between. An example of this would be a robot with a distance sensor attached. If the distance measured is higher than a certain key value, the robot drives straight. If suddenly this distance measured goes below this key value, for example, if the robot is close to a wall, the robot stops and waits until this distance measured will be larger than the key value again. To fully understand this concept, we'll first take a short look at a traditional robot architecture and then clarify the differences to the behavior-based approach. In the traditional robot control system of the time, the individual steps between the sensor and motor were organized one after the other, which is called a horizontal system. This means that once the data has been recorded by the sensor, the robot processes it in several steps. These areas can be summarized as perception, modeling, planning, task execution, and motor control. In other words, all of the recorded data is brought together first. A model is then created using the recorded data. It's important that this can come from a wide variety of sensors and is viewed collectively. This model can then be used for planning, in our case calculating the optimal route, and finally the motor settings can be calculated. The idea behind the behavior-based autonomy is different in this way and doesn't want the tasks to be horizontally structured but vertically. This means that we don't have a central unit where all the information comes together and which then distributes the tasks, but instead choose a decentralized approach. We can imagine it like this. We have many small programs which all represent a simple task. In reality, for example, this could be a program that intervenes when the robot stops and then turns it 90 degrees to the right. Another program could be the one mentioned earlier, which measures the distance in front of the robot and stops it as soon as an object is close in front of it. If we now let these little programs run in parallel and implement this to our robot, we can basically call this our first behavior-based architecture. If we look at how Rodney Brooks implements his approach, we see that he also divides the tasks vertically. Through this vertical division of tasks, Brooks manages to break down the otherwise very complex merging of the various senses and the modeling and planning into many small, simple processes running in parallel. This reduces the needed computational power enormously and creates very fast processing. This is why this application is used in Brooks' small robots, but also in space travel applications, such as in NASA's Pathfinder Sojourner micro rover, a Mars rover from the year 1997, to name just one example. In reality, however, with many different individual programs, this development requires precise planning. This is because the individual programs are often dependent on other programs, which can lead to conflicts and infinite loops. This becomes clearer when we take a look at our robot with the two programs, and always rotate by 120 degrees after stopping. Assuming the robot drives into a three-sided box, it will get stuck in this box forever and turn in circles. This is because after a 120 degrees turn, the robot still has a wall in front of it, and after a 240 degrees turn, the robot still has a wall in front of it, and after a full turn again, it still has a wall in front of it, so it will always turn in a circle. To avoid these errors, such loops must not occur and the individual programs must not block each other. Brooks has developed the Subsumption Architecture for this purpose. This basically does nothing other than create a certain hierarchy in the individual programs and thus prioritize them. If we take a closer look at Brooks' implementation, we can see that Collide and Runaway is the most important. It's level 0. We can also see that the higher the layer, which means the less important, the more abstract the task is. So the higher layers take care of things like object identification and task scheduling. With this setup, the robot doesn't get stuck in any loops or blockades. The system becomes more robust. However, there's one more thing that can be improved in the current system. At the moment, our robot can already drive and no longer gets stuck in loops or blockades, which is good, but the decision-making process is very static. This means that we only ever have a yes or no when we decide things. For example, is the distance to the wall too small? Yes or no. In order to achieve better flexibility here and to adapt the model to human behavior, our model can be extended by fuzzy logic. This makes it possible to not only decide black and white, but also represent things in between. For example, the robot can recognize the obstacle at a certain distance and perhaps turn slightly, or divide the obstacle into groups, heavy obstacle, medium obstacle, light obstacle, and adjust the turning angle accordingly. Okay, so now we have a basic understanding of how the behavior-based autonomy works, and I think this is the perfect timing to show you pseudocode. The pseudocode is from a Mars mission, from a Mars rover called Rookie 7, and this is the navigational algorithm of this rover. We can see that this code is based on many different methods. And each method is there to do exactly one thing: turn in place, thread the needle, obstacle detect, or loop to goal. And we can see that each method consists of one or multiple if statements. These if statements are quite simply structured. If position error is small, go to 1, else turn in place towards goal. And here we see the other thing in these if statements. We do have go-tos, which is not the best standard nowadays, but it makes this code actually quite simple. And if we now compare this to our example, we can see that the approach is quite similar. Okay, to bring everyone up to speed on the current state of the behavior-based autonomy, here's a brief summary of the key points. The behavior-based autonomy is a robotic architecture that moves from the classical horizontal task structuring with a centralized management to a decentralized vertical and parallel mode of operation. This creates robustness and reduces complexity. To improve this robustness, the Subsumption Architecture was introduced, which undertakes a hierarchical structuring. This helps to resolve conflicts between individual programs. Finally, it is still possible to extend and improve the current somewhat static decision-making through fuzzy logic, as well as some other approaches. These are, for example, the Barnes algorithm or the Rosenblatt and Python algorithms. But this might be a bit too much for this video. Now we come to the second half and the topic of intelligent rover architectures. This topic ties in almost seamlessly and involves a further improvement on the relatively simple behavior-based architecture that has been used up to now. The core idea is that the robot should be given the opportunity to remember things from the past, and thus be able to make better and faster decisions when faced with repetitive questions. I would like to present a few of these architectures below to give you a general overview. I would like to explain what a Blackboard is, introduce the three-tiered architecture, the LAS architecture, NASREM, and finally CAMPOUT. The Blackboard architecture is one of the standard ways of enabling the robot to remember. The Blackboard is a high-level operating system that acts as a central interface between the individual knowledge sources and serves as a central database. This enables individual programs to communicate with each other and exchange knowledge in order to be able to solve problems even if their own knowledge may not be sufficient. The individual programs are called knowledge sources and can publish to the Blackboard independently of each other, but can also download data. These knowledge sources can be seen as the experts in their fields. This behavior is organized by a Blackboard supervisor who manages access and uploads and mediates in the event of a conflict. The system works in a similar way to how people from different disciplines would work together in a group. We are all familiar with this model from ROS, where ROS serves as a kind of Blackboard that makes it possible to program with different programs and languages, and to link them flexibly with each other. The Blackboard architecture is then also the transition to a type of architecture known as layered robot control architecture. In this concept, as the name suggests, the processing between sensors and motor control is divided into different layers. The basic form of this approach is the three-tiered architecture. It consists of three levels: planning, executive, and behavioral control. The behavioral control level is the lowest level, which is in direct contact with the world. It comprises reactive feedback control mechanisms that respond to immediate sensor information and makes rapid adjustments to the actuators to react to changes in the environment. In principle, this is exactly the structure we saw earlier in the behavior-based autonomy. In addition to this, however, we have two more abstract levels. The executive level is responsible for breaking down the tasks coming from above, from the planning level, into smaller routines and thus making them comprehensible for the behavioral control level. The planning level is responsible for the long-term goals. It carries out more time-consuming calculations and decides on strategies. An extension based on this general three-tiered architecture is the LAS architecture for autonomous systems. Let's take a brief look at the schematic structure. We can again recognize the three main components of a three-tiered architecture: the functional level, the execution level, and the decisions level. The decisions level is now refined here and divided into two parts: the task supervisor and the plan supervisor, which are then connected to the mission planner and the task refinement, respectively. Additionally, the last architecture adds a request control method inside the execution level. The requests control level checks requests sent to the functional modules and resource usage, acting as a filter according to the current state of the system. If you look at the lower levels, you will notice that the physical system and the logical system appear between the environment and the functional level. These two categories are not explicitly mentioned in the general three-tiered architecture, and are listed here because the last architecture specializes specifically in autonomous robots. If you take this model further and further with more and more levels, you will finally arrive at the architecture known by the National Bureau of Standards, the NBS, as the NASA NBS Standard Reference Model. Although this architecture, which later becomes known as the Real-Time Control System, is only a theoretical approach and not a concrete implementation, it plays with the idea of an almost infinite number of levels. The lower levels, which are responsible for the basic movement commands and are closer to the environment, have a high cycle rate of 10 to 100 Hz. The further up you go in the levels, the more general the basic tasks become, and the cycle rate also increases until it is more than 10 seconds at the top level. Okay, we've now spent a long time talking about possible architectures that could be considered for individual robots. NASA's JPL, the Jet Propulsion Laboratory, has now developed a structure that is also based on the three-tiered architecture, but has been specially developed for multi-robot systems. The architecture is called CAMPOUT. Here we can directly recognize our three levels. The more advanced interlocking of the levels and all above the connection to the other robots is noticeable. We can see that the lowest level, which sits directly above the hardware interface, not only consists of reflexes, but also contains a section for communication with other robots. Of course, you might ask yourself why communication takes place at such a low level and why it doesn't take place in a higher level. But you can understand this quite quickly after a brief example. If you imagine two robots with gripper arms lifting a bar together, then it is essential that these processes are carried out simultaneously, and that they have a very high precision. And remember, lower levels have a high cycle rate, higher levels have a lower one. This high update rate in communication is very important for the team to work together. Let's come to the end of the video and provide a concluding summary of the topic: behavior-based autonomy and intelligent rover architectures. Basically, it can be said that behavior-based autonomy lays the foundation for the methods of intelligent rover architectures presented here. The behavior-based autonomy moves away from the classic horizontally structured processing chain of the robot towards a vertically structured and parallel operating chain that doesn't require modeling of the entire system, making it more computationally efficient. To enhance the behavior-based approach and give it the ability to learn from past experiences, intelligent rover architectures build a sort of memory on this basis. The most important aspects here are the Blackboard architecture and the basic form of the three-tiered architecture. In this setup, the underlying structure essentially corresponds to the behavior-based approach, which is controlled and supplied with information by abstracted knowledge in the higher layers, thus extending the improving of the behavior-based approach.